All right. So welcome everyone to the SFU Sports Analytics virtual seminar series. Today we have Dr. Frank Imbach, who's affiliated currently with Seenovate and also from the Unité Dynamique du Muscle et Métabolisme at the l'Institut National de Recherche pour l'Agriculture, l'Alimentation et l'Environnement, as well as the Universite de Montpelier. Dr. Imbach is trained primarily as a sports scientist, but he has a strong emphasis on computer science and statistics. He holds bachelor's and master's degrees in sports performance engineering and a PhD in exercise physiology. He's also certified in nutrition counseling, and he's worked as a performance trainer for the French national kiteboarding team for approximately 7 years, which is a sport that he also practices at a modest level. Dr. Imbach's research focused on the effects of training on athletic performance and injuries through an interdisciplinary approach that blends sports science and computer science. Currently, he works as the lead sports scientist at Seenovate, a digital service company in which he leads the sports statistics department. His research activity has slowed down a bit in the past years since he graduated from his PhD and has transitioned into industry, but he's eager to refocus it in the coming years, starting today with our seminar series presentation. So today's talk focuses on the rapid technological progress, in sports and how it's been a game changer and has significantly impacted practice. Monitoring an athlete's effort is now relatively straightforward and has revealed new perspectives of research applied to performance. In this seminar, Dr. Imbach will discuss the relationships between training and athletic performance for training optimization purposes. After summarizing the main approaches for modeling training load responses on performance, he will address 3 key points. First, the training load quantification for athlete monitoring. Second, the evaluation of performance. And 3, the methods used for mapping both. He will show how computer science could help solve sports performance issues while bringing insights to athletes, coaches, and support staff. The limits and perspectives of each approach will be highlighted and discussed. So once again, thank you so much, Frank, for joining us, especially in the evening time in France. And we really look forward to hearing what you have to say. So I'm going to stop sharing and turn it over to you.
Okay, thank you very much. Did you see my screen? Is that all right?
You're currently on
full screen?
your note screen, Frank, so I can see your notes and stuff.
Okay, ouais. Just fixing it. Up. It's a bit tricky, but I'll manage. So you have the full desktop, and I think it's the same if I do this. This way, and you have the 3 screens.
So we just had your now you're back onto your note screen, but we had your previous screen was working.
Okay. Sorry, I'm searching for the solution.
It's okay.
It should be easier with notes. Even it takes a few minutes. Okay, this one.
There we go.
And now?
Yeah, perfect.
It's good? Yeah, nice. So thank you, Dave, for introducing me. And I'd say it's a pleasure for me to give this talk and to be part of such a nice webinar series on sports analytics. So thank you for that. Before beginning, I would like to apologize for the grammatical mistakes I could make, and I will make some for sure. So just be please indulgent and feel free to interrupt me if needed during the presentation, during the talk. Okay, so you clearly summarized, but the work I am going to present today rises from a collaboration between the 2 labs. You cited ULMOVE Digital Health in Motion and IDM, which is mostly involved in muscular dynamics and metabolism. And the company Seenovate, which is the digital service company, I'm still working actually at a position in the company. That means 3 entities and 3 domains, scientific domains. which are sports science, mostly driven by the two labs, and mathematics, statistics, and computer science by Yellowmove and Seenovate. So we will start with the big part of the talk, which is the training loads. I'm sure most of you know what is a training load, but we'll take some time to recall it and to put some definitions about the terms. So I put this definition, I dropped this definition right there. Training load could be a quantitative or qualitative representation of the effort produced at exercise. The term load has no mechanical sense. This has been discussed very clearly with Stoughton and al. Last year. And in training loads, we have two dimensions. The first dimension is the internal training load, which could be defined such as the physiological stresses imposed on the athletes in response to the external load, and an external load, which is the work completed by the artist independently of his internal characteristics. So for the objective training loads, the data or the variable are mostly quantitative. I mean discrete variables or discrete data, such as data which have a finite value, and continuous data such as the age, the height, heart rates, measurements, and mechanical works, energy, and so on. For subjective training load and qualitative or categorical data or variable, we are mostly on the two parts, the two sides of this data, such as nominal data, we could say the type of training, and ordinal data, such as any visual analog scales, such as RPE. So the first question could be, what amount of effort has been done by the athletes, and what does it really mean, among others, in terms of physical adaptation? So we have different manners to measure training loads, objective training loads. And first, we will start with endurance sports with physiology-based approaches. The first one comes with TRIMS, so the training impulses initiated by Bannister in 1985, in which exercise intensity it's based on heart rate, so exercise intensity, and more precisely, a fractional elevation of the maximal heart rate, the session volume or the exercise volume, which is characterized by the exercise duration, and an exponential weight that accounts for greater taxes and adaptations involved by high intensities. You can see the K here in the equation, but don't spend more time on the equation, which is based on blood lactate concentrations. This constant term has a proper value for male and female, which can make the difference between the two populations. These training loads or TRIMS are still used today and have benefits for quantifying training loads in continuous exercises or training phases, long training phases, but only suitable for submaximal intensities. So a few years later, we had some alternatives and extensions of the Bannister training loads, with first the Edwards training loads, which is more suitable for intermittent exercises, but still at submaximal intensities. In brief, Edwards just split a factor K according to 5 levels based on an intensity range, still based on the heart rate, to more represent the load induced by the body or to the body during intermittent exercises. The negative point, if I could say negative, is the model has a linear weighting across intensities, so it neglects the nonlinear effects of physiological responses to exercise above lactate thresholds. And we have also an extension I don't mention here, but an extension which includes an exponential weighting factor. So just see Stanio et al., but I don't precise it here. A bit later, 6 years later, Lucia et al. Also did like a model really close with 3 levels, but not based on heart rate, but on bulk lactate concentrations. It's suitable for intermittent exercise, still at the maximal intensities. But 3 zones could induce an unclear representation of the real exercise intensity performed. For example, a similar value could be given for both lactate threshold and maximal aerobic power. So that's why I say this model is more suitable for some maximal intensities. And the relationship between levels is still linear. And another one, the last one, alternative to the Bannister streams, comes from Yujika and al., which is more suitable for all intensities and intermittent exercises, still based on lactates with 5 levels and has a linear weighting across intensities. This method is based on a correspondence table on the individual lactate velocity threshold. So we can say it is applicable in most conditions. Out of streams, we have the Imbach, which is famous these days, which is impacted by the exercise intensity, duration, and modality of exercise. It has several factors responsible for an epoch raise, such as the ATP and PCR stores with synthesis, cytokine release, and so on. And it brings light onto the importance of post-exercise monitoring. Among the raise factors, we could say also energy cost, yes, and also cytokine release, and also inflammatory responses, which could be very interesting if we take a look at the individual responses to exercise. So I just put drop right here a take-home message from this. Heart rate has a key parameters for estimating exercise intensity and therefore training loads, because training loads include exercise intensity, of course. Heart rate holds numerous drawbacks, such as it is mostly suitable for steady states of maximal intensities, and it is influenced by the environment, temperature, and so on, and the subject itself, the athlete itself. But it's still allow for estimating training loads objectively, and it's still used these days. Last one, if I'm right, is the training stress score. So a bit less physiological or physiology based. It is based on power output and an intensity factor, IF. It gives an individualized index that allows for inter-subject comparisons or inter-athletes comparisons, and it is also generalizable and as homologs. For example, we have the RSS in running, and if I remember, we also have one in swimming. Just to explain what is FTP. FTP is a functional threshold power, so the power value that could be theoretically sustained and approximately 60 minutes. Okay, so now we were on external factors, sorry, and now we go through internal factors. And we could say we have look at hormonal responses, which has been widely used since 1980 and maybe before, such as testosterone responses, growth hormone, cortisol, and so on. indirect biomarkers, sorry, of muscle damage, such as creatine kinase, C-reactive protein, and tumor necrosis factor, and cytokines, such as well-known interleukins, IL-6, and so on. The goal is to find an indirect estimate of physiological stress induced by resistance training. So yes, I should put this bit. It's mostly dedicated to resistance training. So we can ask, what about the training load quantification, more precisely? And in resistance training, the main method is the so-called the volume load. So it's not from half, but he did a nice summary. In volume load, you have V and L, volume and load. V multiplied by intensity, while intensity can be in absolute value or relative in a percentage of repetition maximum. The big issue with this method is that volume and intensity are reciprocal. So that means if you lift 10 reps at 100 kilos, it is equal in terms of body responses or physiological responses to lifting 100 reps at 10 kilos. So it's obviously not the case, but it's the main drawback of this method. Some alternatives has been provided to tackle this issue, such as holding repetitions in reserve, and alternatives based on RM predictions equations for a given number of repetitions. But the main limitations underpinning volume loads persist in terms of real physiological meaning behind the model. Also, we could say the volume load in this form does not account the load travel, so the distance traveled by the barbell, which could be applicable to mostly situations, and we could also estimate or compute the mechanical work which is affordable with a low cost these days with the technological ways improvements. Also, it doesn't take account the recovery, the intersect recovery durations, since it's still an influencing factor of physiological adaptations. We have some literature on this and some studies on hormonal parameters such as growth hormone, some cortisol and lactate, and so on. But Marston, 6 years ago, proposed a density aggregate. So it tackled this issue easily, but it's still to be studied. And the last one, I would say the time adaptation, which is clearly not included in the traditional volume load or repetition velocity. Today, the VBT has a big part of training, so velocity-based training, sorry, and time adaptation is a key factor of exercise response, so we should consider it when estimating training loads in resistance training. Final note with VBT advantages is that it can tackle RM-based programming issues, so RM fluctuations and invasive 1RM testing. It accounts for individual differences using their own load velocity profiles, and it provides feedback to the practitioner and offers valuable absolute loads according to individual load velocity profiles. So VBT was the cost. I think yes, at least it should be considered. Okay, now we move on the field. So the first thing I should say is that the technology, the rise of technology, just brings so much web systems such as GNSS and so on, which leads, as you said in the introductions, which produce large amount of data we are dealing with, and this data are mostly used for estimating training loads externally. This is the case for GNSS, Global Navigation Satellite System, and LPS for the local ones. Even if we have a synchronization with some physiological measurements, for example, heart rate monitors, synchronized with GNSS. And for the GNSS, we have so position-derived data such as distance, velocity, speed. So we have the volume and the intensity parameters for training load calculations. And each brand provide their own metrics. If you take, for example, Catapult, which brings the well-known player load, dynamic stress load, and so on. It's just so many features proper to companies, but still interesting. So yes, we have more data, more features, and mostly summarized statistics. So this is a statistics for one session. And it brings to us a multidimensional approach of exercise demand. So in summary, objective training loads are valuable for estimating stresses imposed on the body, and external estimations such as physical are applicable in most conditions. But physiological responses and external training load relationship is not straightforward, and it can lead to a misunderstanding of the athlete's response to exercise, mostly due to a lack of physiological evidence behind external training load indexes. So now we are going to discuss and to present internal training loads and mostly subjective measure of training loads. So I'm sure most of you know this table, the RPE from Borg, the old one, which is a scale that ranges from 6 to 20. So this is how much was difficult the exercise. In terms of function, it's a linear growth function with regard to either big demands. So naturally, it's mostly dedicated for endurance exercises. And then we had alternatives or extensions to, yes, I would say alternative, it's better but to this scale, this 6-20 scale, with a category ratio scale that range from 0 or 1 to 10, which is now a non-linear and positive accelerating growth function. This one is more suitable for high intensities and strenuous exercises, and also which is mostly used in resistance training, and not this one, which is more endurance. And a last one, which is close to the category 10, is the 100 version. That brings only a larger range and so more variability in the responses. And it tackles some common use of whole numbers only in the category 10 scales, causing deviations in the stimulus response functions. So the purpose could be to estimate physiological and psychological stresses concurrently from subjective measures of training loads, such as an overall response to exercise. I think this sentence makes a big difference between objective measure we saw just before and subjective measure of training loads. Okay, we we presented the input, the entry of the system, but now what about the performance? So athletic performance could be an individual performance that involves physical skills. This is a definition and not the only one, but it's about finding a performance criterion. Finding a performance or assessing a performance in ecological condition could be a very big deal. The method should be non-invasive because tests can be risky and it could impair training programming or planification made by the coach. It should be daily for the best, or at least weekly measurable and transferable to the discipline. It also implies a rigorous assessment on at least two sides. The first one is about the assessment of the data acquisition. So the consistency of the process, standardization or standardized collection, and robustness and regularity in the collection. And also on the data storage, so the timely storage and an efficient database or suitable architecture in order to fulfill the requirements related to what we would like to achieve in terms of statistical analysis or data visualization, for example. So, as I said, measuring athletic performances with consistency remains challenging. And now we will end the introductions with maybe the biggest part or the modeling part, at least, with a review of some models which are developed to map the inputs or the training loads and the athletic performance. The first one and the oldest one is the fitness fatigue model, initially developed by provided by Bannister in 1975. So I just showed the diagram of the simplest configuration or formulation of this model. It comes with a discrete function, omega t, that usually represents a training load, be it objective or subjective, as you want. Then a first order transfer function gives two impulse responses, so two states or two features, which are called fitness and fatigue. The difference between fitness and fatigue gives a performance at time t. Yes, this is very simple configuration, and some years later, some extensions has been provided. Mostly the first one, not the first one, but a big one with linear time varying models. This one is time invariant models, so the parameters do not change across time, and multi-component models. In linear time varying models, I cite Busso in 2023. And we also have deterministic models. This is a deterministic model based on a strong physiological and empirical assumptions, evidences, so that we say that the response follows an exponential function that yields to the performance. And last thing is that such models are interpretable, so we can interpret the parameters and their evolution in the modeling. So we are trying to explain a complex phenomenon, which is the athletic performance, in our case, using a single input here, and based on a strong and expert hypothesis. So keep that in mind. A bit later, we have different approaches, which are more statistics oriented with linear mixed models from Avalos and Philippe, which allow for training a model over a group of athletes, an entire population, and using random effects for matching singularities in response to training, we can consider inter and intra-athlete variability. Purpose is to draw a population difference from data upon rigid assumptions, so linear assumptions, and to give an explicit understanding of how a system, in the case of the model, or how an athlete behaves. And at the same time, a bit later, and nowadays, we have the computer sciences, which comes with finding a generalized predictive patterns upon minimal assumptions in terms of statistics, intended for making future predictions of athletic performances. When I say generalizable, yes, we have a big care about model generalization. So a model which is able to predict accurately on training data or data, known data and unknown data. But we'll see a bit later. And we also have a craze for artificial neural networks. For example, I just cited the first one in 2022 and Mitchell in 2020. Such models or model family have high predictive power and can match nonlinear patterns, but also need a larger sample size and the model parameters cannot be interpreted. These are black box approaches. I will close the introduction with the last slide about this question: are we doing artificial intelligence? So artificial intelligence could be defined this way, or we could say that it enables the machine to think like a human, and continuously evolving and very difficult to grasp. Machine learning, which is a part of artificial intelligence, refers to automatically learn and improve from experience without being explicitly programmed. And deep learning, which is a part of machine learning, it's about mimicking the human brain and gradually increase the level of abstraction through a layered configuration. The big difference between both in that between machine learning and deep learning is that in machine learning we have an operator, a man who's doing feature extraction by hand. Whereas in deep learning, the model do all the process itself. So in machine learning, we can interpret, we can see deeper in the model, and we can configure the data set for modeling as we want. For example, bringing physiological evidences in the dataset building. But in deep learning, this is a big mix, and the black box is right here. It is powerful, but there is no people to specify this data or these extracted features when it comes to another data set which could be used for modeling. This is a difference. And also deep learning needs larger samples of data. Yes. And we can see learning as an optimization problem. So finding a joint parameter configuration so that the error is low, the error in prediction, I mean. It's like a turning button so that machine will say, okay, this is a car and it's not a plane. So you find the best configuration to limit the error. And how to do that? We have mathematical tools such as gradient descent optimization. It's just moving the parameters from right to left and so on to find this point of convergence and to find the minimal value for the loss function, so the minimal error. And it is learning, it's naturally inspired. For example, you can see at the left side of the panel a beautiful function applied to insect, or I don't know, insect or bird swarm, which has his homologue at the right with a sphere function. It's the same. In any case, values converge towards a precise location here or here that minimize a cost function such as energy or whatever. And in biology, we have the biological neuron. So again, it's definitely naturally inspired. For example, with electrochemical conduction through the neuron, where information comes from the dendrites on the left and is carried through the neuron until reaching the axon termination. So the process is the same when we talk about artificial neuron or neural networks with somewhat more mathematics or math formulations. So now I will drop some questions. One main question on main research issue, which is understanding relationships between training and athletic performance for optimizing training plans. And 4 secondary questions with how to improve the determination of training indexes in resistance training. What is the value of features provided by GNSS, or more largely wearable measurement systems companies, and how to get new features from exploited raw data. What about generalization capabilities of fitness fatigue models, an essential condition for physiological empirical interpretation of model parameters? And the last one, how athletic performance could be assessed through the use of robot sensors in a non-invasive and ecological condition. So we start with a first study, first example, with the following purpose, which is to provide a new model of training load quantification based on observed physiological responses to resistance exercise. So this is the experimental setup. We have four testing sessions, 15 participants, amateurs or professionals, professional athletes that train at least 3 times a week. This was the condition. And the 4 testing sessions start with the gray one, which is a torque velocity profiling on an isokinetic dynamometer. So from this session, we get linear profiles to exponential profiles. They were very heterogeneous. And then we have three sessions which were theoretically volume equated. These 3 sessions are 3 resistance exercise sessions performed in randomized order, with the first one a low intensity session with one set of 24 reps at 58% of the maximum voluntary contraction. The second one is 2 sets of 9 reps at 77. And the last one is 5 sets of 3 reps at 93% of the MVC. Which is very important is that individual intensities and number of repetitions were found according to the exponential relationships between the relative intensity in percentage of maximal repetitions of 1 RM and the number of repetitions before failure. This way, the 3 sessions were, so as I said, theoretically volume equated if we consider the famous volume load equations given by the product of volume and intensity. We also measured some physiological responses, and we will focus only on neuromuscular responses, such as rate of force development, EMG analysis, and in both time and frequency domains. So for the first result, we can see that in time domain analysis, the rate of force development, we know that it is a key indicator of muscle fatigue. And we see a across the three conditions or the three sessions. I recall that the first one, C1 or condition 1, is the low intensity session. The second is a moderate intensity session, and the last one, the third, is the heavy load or high intensity session. And we can observe a greater rate decay of rate of force development, peak RFD and 100 RFD for high intensities. High intensity exercise are also the slowest exercise because we call that we are in an isokinetic setting. So there is correlation with between intensity and velocity. And we also see a greater variability in the responses, in the RFD responses. I mean, rate decays ascribed to this condition, to the third condition, explained by significant differences in time passed at exercise. For example, one athlete could perform the exercise at 10 degrees per second, and the other one at 30 degrees per second, still based on individual torque velocity profiles. In frequency domain analysis, we see the same results from the power spectrum. Big correlation between median frequencies and rate of force development, where high intensities show the greater variability, but also greater magnitude of neuromuscular impairment. So based on this observation, we have a singularity in response to, in the responses to resistance exercise predominates at high intensities. So the question is, should we exercise muscle-induced fatigue, include muscle-induced fatigue in the training load quantification? And I think we have a small idea. So to consider muscle fatigue in the training load quantification, we provided one main basic formulation of a new model and two alternatives. And the first one, it is based on this figure, which is the relationship between rate decay of RFD. We took the peak, but we took the 100 milliseconds. So the relationship between this and the intensity, relative intensity. So we have an exponential relationship. The first one, so this is just the product of volume and intensity and this factor which include alpha, which is the slope of the relationship. The first alternative is a density correspondence, as Barston did in 2017. In which you see here we divided the training load RFD by R, which is the total intercept recovery duration. And the last one for the alternative using impulsion, it's just another way to tackle the volume and intensity parameters with a measure of impulsion. So, okay, here we comes with the idea of compressing the information in a single measurement. So first, we proceeded to a principal component analysis, which is a linear combination of training load quantification methods and training related variables. Just here on this figure, we will comment it, but the blue ones are out of the PCA because it represents the physiological response to exercise. And we can see 81.5% of the total variance is explained by the first two principal components. The cycle of correlation shows on the left side objective training loads according to density features. So density VL, density MDL, RFD, and so on are uncorrelated with subjective training load estimates, mostly session RPE, with a category ratio scale or just the RPE. And in addition, this density features or calculation of variables are also correlated with raw features or raw RFD features and impulsion. We also know that the volume load, which is in blue, is very small and sadly explain an insignificant part of the total variance. If we look at the projection of individuals, we can see that the physiological response are diametrically opposed between low intensity, which is in blue, and high intensity, which is in red. So we have clearly three groups following the clustering, which corresponds to the intensity of each conditions. So they could be mainly discriminated by only the first component, while the second principal component informs about the dispersion. The dispersion, the individual differences within a group, yes, for each conditions. So the individual physiological responses to each protocols. And if you look at the explanatory power of training load indexes on this table, we see that at the top of the table, we have the subjective measures, RPE and the category ratio are likely better for estimating physiological adaptations in a linear way. Whereas session RPE is definitely failed in this task. It questions the pertinence of an exercise duration rating, I mean session RPE, particularly because since RPE alone does already account for a time dimension, that means the duration of exercise already influences your RPE rating. So should we consider keep considering session RPE or not? I don't know, but we can question. And we have objective measures at the second part of or middle part of the table with VL, volume load, and density alternatives of volume load, which are not good at all for both. At least a bit better for density volume load, for explaining each of these physiological responses. So I recall lactate, blood lactate concentrations, the rate decay of median frequencies, rate decay of RFD, peak, and 100 milliseconds, and the energy, EE. And on the last, at the bottom, we have the first PC, dimension 1, which is the first principal component, which gives, as well as training loads, RFD, our models, definitely outperform the other indexes we saw just above. It supports their interest in estimating physiological responses as a training load index. So here, just a point, don't care about stacked point DIM. It's a meta model built from coordinates of the two first components, principal components, but it's a bit out of scope for this example, and have some practical issue. So in conclusion, a composite representation of training quantification methods, including the physiological based and some unexploited training related variables, looks particularly promising. I will pass very quickly with the discussion and conclusion. We have a strong application of the muscular profile in the physiological response. One of the limits is that we focus on monoarticular exercise, which is a kinetic concentric condition, and polyarticular exercise might lower the influence of the difference of between profiles, I mean linear to exponential, and their influence on the physiological responses. The exponential weighted model should be applicable for quantifying training loads in any resistance training sessions. And in a monitoring process, training loads indexes should always be considered with other training-related factors that might impact the athlete response to training. Now, I will call the questions and propose the need for assessing the general solution capability of impulse response model or fitness fatigue models. Can we really draw physiological and practical interpretations of model parameters? So in this study, we aimed at providing a transferable, robust methodology which relies on a model generalization in the context of sport performance modeling. We had seven people, 7 short track speed skaters at highest level, Olympic one. The target was a time trial over one lap and a half. And the predictors, if we summarize, were objective training loads, objective parameters such as maximal power, average power, and the session duration, density, and so on. But and also environmental parameters such as ice quality, rest, and the past performance, and the athlete, of course. And we just take a look at this one. We computed 2 kind of cumulative responses from raw training loads, which can be represented here. For the first one, it is just an impulse response aggregation as done in a Bannister model. So it is just an exponential aggregation with an exponential decay over time of the value. And then we computed a serial B exponential aggregation, which benefit with some physiological adaptations such as tissue remodeling, fiber shortening, velocity, and adipose activity. So we have an increase just right after the training, and then a decrease over time. In this figure, the vertical dotted line represents each training sessions, while the points represent each days, with or without training sessions. So the question was how to consider information from several training sessions for explaining a future performance. So we included each aggregations as predictors in the model. In terms of model, we computed 4 models with the variable response from Busso, which is an alternative an extension of the fitness fatigue models, as the reference, and 3 other models, a linear regression, multivariate, with a penalization or regularization, which is an elastic net model, a principal component regression, and a random forest. We had 19 predictors, 248 observations, which is very few. And so we can say we have a high dimensionality regarding the sample size, multicollinearity between predictors, and we computed all these models, excepted the variable response, either on individual and on the group. An important part of the modeling is the validation of the model. The performance variable is not independent and identically distributed because its probability distribution function depends on historical data. In other terms, the performance at day, for example, 50, depends on the previous performances. So in brief, we had this approach. We split the data, the full data, into 2 data sets, with 80% of the data for model selection and the remaining data for model evaluation. In brief, the model selection on the left side, we split the data in n subsets. In each subset, different combinations of hyperparameters are tested. Each model, so a model with a particular set of hyperparameter, is calibrated over training data and validated or tested on subsequent data, so green and yellow. We repeat it n times using an incremental window, so the training subsets increase for each new iteration. And by this way, the time order is kept all along the process. This is the most important. After that, the best model is retained. And the best model is a model with a set of hyperparameters values that show the lowest error rates when making predictions on the validation subset in average. And now comes the model evaluation at the right. We retain the model on the training and validation subsets to test on unknown data in red right here. And that ensure robust evaluation of the model and comparisons, and allow for comparisons. In terms of results, we make the difference between results in terms of generalization. So the difference in accuracy between training data and testing data. We see that the best models were the elastic net computed on the group, on the overall population, and the principal component regression, whereas the random forest was the worst model. So the random forest suffer from overfitting issue. In prediction, we see that elastic net is also the best model, which has the lowest error rate. And also the response, so the kind of fitness fatigue model was not so bad. It had maybe one of the highest error rate, but it had also the highest R2, so the coefficient of determination. And we see an applications of the two best model versus the dose response in dashed line here. We see that the impulse response model provide a kind of smoothed prediction, whereas the two other models try to fit performance and counter performance. I recall that this is a time trial, so the best performance is the lowest point. And we see the standard deviation is way lower for the dose response than elastic net and the random forest. So we can say that training load has a weak predictive power because it's kind of average or mean model. And in the elastic net, one point is that we have a high influence of the autoregressive component, so the past performance over other features. In terms of generalization capabilities, the multivariate approach is naturally highly recommended for athletic performances modeling purposes because athletic performance is a complex phenomenon. And combining athletes for greater sample size and performing regularization procedures is interesting. It allows for dealing with low sample size issue and multicollinearity between predictors. The limit of the study, I just dropped two limits. We had non-measure impacting factors such as athlete buy-in, motivation, cognitive function, and so on. So it questions the importance of measuring the right variables. What are the right variables? And are the data fully unbiased? Not without taking into the details, but we should let a space between training and testing data to be fully robust. In conclusion, impulse response models for predicting athletic performances, these models suffer from their univariate configuration, but their mathematical structure remains simple, advantageous for drawing interpretations from the model parameters, and should be only slightly prone to overfitting issues. In perspective, we have detecting key factors of athletic performance from multivariate analysis, which is an essential insight for coaches, and from multivariate models, we could perform conditional simulations to find the best sequence of training sessions or the best protocol. just a note on fitness fatigue models. Their strength, the strengths of fitness fatigue models relies on this deterministic model, interpretable, as we said, and their structure, their algebraic or analytical representation of an optimal command. The optimal command is a training load. So it is a controlled theory. So controlled theory means there is no simulation needed for finding the best sequence of training, just some equation manipulations and solving. Their main drawback is that they suffer from univariate configuration and simplification or simplifying assumption of a complex phenomenon, such as athletic performance. So what to do? We could propose to extend the mathematical structure of fitness fatigue models to multivariate structures or multivariate alternatives, and benefit from machine learning methods such as ensemble learning. In brief, I just show one method among others, which is stacking generalization or stacking. In this method, it's simple. We have a data set X of M variables and N observations. Some models, model 1 to model P, and P capital. So the first models could be fitness fatigue models or alternatives. So univariate models with a strong hypothesis from physiology experts, for example. And the other models could be machine learning models, multivariate, that consider environmental information and so on. Prediction from all models build a second data set that comes as input for meta model M here, which will make final predictions. So this is an approach which could be interesting and which could be tested. I'm actually working on this one. And I see we are close to the 60 minutes, so I will be very quick for the last part. We have 10 slides more. The last questions were, are the GPS commercial features relevant for athletic performance modeling? What to do with GPS raw data, and how to detect athletic performances through wearable sensors without making any specific test. So we put the purpose, the following purpose, to address the research questions through different predictive approaches. In terms of data, we worked with the football club of FC Lucerne, which is in the Super League divisions, and made a follow-up over 1.5 season, 2019 to 2021, and we had 196 training sessions, 74 games, and 42 players, considering regular ones and new hopes. This is a summary of the data set. So just in brief, we have the distance, total distance, high intensity distances, acceleration across some thresholds, decelerations, also sprints, and the player. We did an aggregation because we tried to predict a game using data from the previous sessions. So we took 5 events, practice, 5 practice sessions to predict the 6th event, which is a game. So the question was how to aggregate this data to consider information from training to predict the athletic performance of the game, of the following game. We did 2 methods. The first one was just to compute the average of the 5 sessions for each variable. And the second one was to compute an exponential weighting aggregation according to softmax function. So take, for example, on these plots, on this figure, you have the first day per game, the value is maximal, and it decreases over time exponentially. But I said we will predict an athletic performance, but what is the performance, and how to measure it, how to assess it? We relied on a proof of concept by Morin et al. In 2021, in which JB Morin computed acceleration velocity profiles from each games. So we adapted this method to our data and provided three modeling tasks to predict the coefficients of the model. So the intercept and the slope. The three tasks were a time series forecasting, which is our baseline, which consider only data from the acceleration velocity profile, and a multivariate modeling from commercial features and a multivariate modeling from GPS raw data. So task O and 1 are control task and time series forecasting. The control task is just a prediction of the profiles from commercial features of the same game. I pass this one. We use different methods of time series forecasting for predicting games data using only acceleration velocity coefficients and no covariates. For the task 2 and 3, we computed the model over the group, over the population, and over individuals. So individual models perform K-fold cross validation, proceed to a feature selection to 10 features, and the third task was exclusively built above raw GNS data. So this is a summary. We compute a ridge regression with average regression or exponential smoothing, and LSTM is a long short-term memory neural network. In brief, it's a recurrent neural network that saves past information from the predictive outcomes. And for the third task on raw data, we extracted features from time and frequency domains, which leads to a lot of features, which reduced to only 10 with feature selection. And what we see is that first, the control task, commercial features from games to predict acceleration velocity coefficients of the same game provided a lower error rate, which is good because we can say that the target is predictable. But we also observe non-significant differences between intercept and slope predictions. So it's not easier to predict the intercept than the slope. It's the same, likely the same. And no significant differences between group and individual computed models. So we saw in the last study that computing models on group was advantageous or better. It's not the case in this study. And also, we have no differences between the aggregation methods, such as the average and the exponential smoothing. So maybe that means that, yes, that represents a lack of explanatory power of the variables. In conclusion, there are only slight differences, even not significant in terms of accuracy among all models. Neither commercial features nor features extracted from raw data outperform the time series model, which were the baseline models that use only past performances. So the question is, are the training data informative in-house, or is the opponent's influence too strong? However, models provided an accuracy between 7 and 10%, which could be considered as low. So this is not a bad thing or bad results. It was efforts in light of unconsidered performance influencing factors such as technical, environmental, psychological, and the opponent, of course. And in conclusion, I recall the questions and give some answers here. How to improve the determination of training load indexes in resistance training. So weighting the exercise intensity factor by physiological mechanism, muscle fatigue, and neuromuscular function impairments. Using data compression methods, so using principal components for making the most of training load indexes and training related measures were interesting and maybe a good approach to study a bit deeper. What is value of features provided by GNSS systems and how to get new features from unexploited raw data. So responses answers are built from empirical evidences. We have a limited value for predicting acceleration velocity profiles. So lack of informative and explanatory power in this case, considering this target. And features extracted from raw data, time and frequency domains, open new perspectives using, for example, IMU, inertial measurement units, data for aesthetic performance and injury occurrence. Because we had the same performance using this data than the commercial ones. What about the generalization, the capabilities of fitness fatigue models? Is it a necessary condition for physiological empirical interpretation of model parameters? Yes. And based on our investigation, this model only slightly suffer from overfitting issues and behaves like a moving average-based model. Physiological empirical interpretation should be conducted in light of model prediction capabilities. And for the last one, how athletic performance could be assessed through the use of wearable sensors in a non-invasive and ecological condition. Yes, the acceleration velocity profiles modeled from GPS raw data looks valuable, but the opponent activity still has to be considered. In perspective, an analogy to TRIMP, to the training impulse in resistance training using physiologically weighted training load indexes and its application for athlete monitoring. Extracting features from inertial measurement units, embedded sensors for athletic performance and injury occurrence modeling purposes. And the last one, as I said, extending transfer functions used in fitness fatigue models to more elaborated functions, such as high order, state dependence, and interactive model structure to validate, for sure, these models in a physiological and statistical way. I'm working actually on these 4 points, so stay tuned. Thank you. Sorry, I was a bit long.
Not problem. Thanks very much, Frank, for that talk. You definitely covered a lot of ground, and give us a good education on modeling of training loads and performance across a variety of sectors. So just you covered endurance training, resistance training, and intermittent or field-based team sports, which is the 3 major sectors of sports science, really, at least as I see it. Yeah, that's quite an impressive body of work that you have there.
Thank you.
I'd like to open up the discussion or to questions from the audience. And so just feel free to chime in or to unmute yourself and ask away. Turn on your video if you don't mind, so Frank can see you. Maybe I'll start with one. So you talked about the Edwards and Lucia Trimp formulas, and you made the nice points about how they're linear in terms of intensity impact. You said
Yes.
that these are more appropriate for intermittent exercises compared to the Bannister model. And I was just curious, like, I know you explained it, but I kind of missed it. Could you just go over that again? Like, why are these 2 Trimp formulas more appropriate than the Bannister formula?
Okay. Yes. I will share my screen and go back on the slides. So it was in introduction. So we have the Bannister one, which is, so Bannister, okay, this Trimp is suitable for the maximal and no, yes, and endurance exercise. You mean, Edwards, because we have a split and a split approach of intensity on 5 levels. So we can compute like the streams for this range of intensity according to heart rate. So 0.5 to 0.6 and so on until the maximal one.
Yeah.
And in the Lucian's one, it's the same, but it's just a downgrade of 1 to 5 to 1 to 3, but it's still the same approach.
Yeah, but I think, like, I'm just curious though. Have you ever looked at computing these metrics for like high intensity interval training workout, because I mean, ultimately what's going to happen is that you have your bouts of high intensity where the coefficients, the high
Yes.
end coefficients are going to be emphasized, but then you also have the recovery periods, which will probably make the average heart rate about the same anyway. So I'm just like, I think in principle, like theoretically, yes, they look more appropriate for intermittent exercise, but I'm wondering if actually in practice, whether you get much difference in the overall TRIMP values once you consider the whole workout.
Yeah, I just used in a study with runners the Bannister streams because it was about running, and I didn't try the other methods, so I cannot answer what are the difference or the magnitude of the difference between the each methods.
Mhm.
But I think the most important is the difference in the approach in the model, and we should take the best approach for our practice, our context.
Yeah, of course. Yeah. Great. Thanks. Next question I have, and again, feel free anyone to jump in, but for the resistance training equation approach
Yeah.
that you supplied. So, we're doing quite a bit of work in looking at training load functions as well, and I think that your use of like an exponential weighting function is makes a lot of sense. The question is, so how would you go about using this equation for someone for whom you don't have physiological data? So like, and again, and I apologize if I missed it, but you've got these functions that you had, but you had like a very comprehensive data set to,
Yeah.
put numbers to that approach. Now, could you just take that approach for an individual for whom you have no data and use it? And if so, how would you use it?
Yeah, of course. I should zoom on this one, on this value alpha. It's the same like it's an analog to the trim because Bannister provided an alpha his model, one for men and one for women, and it's the same in our case. Okay, we had enough data to compute this relationship above our population, and for example, you can train tomorrow, and you can compute your own training load using this coefficient. Okay, so this is we provided here a generic coefficient. So okay, it's only based on 15 participants and a heterogeneous population. But in average, these coefficients model this relationship, sorry, and anyone could use this value to compute the training load.
Gotcha.
So this is a generic approach.
Okay, so you
But
could, I mean, if people had the same experimental setup, they could
yeah,
fit their own, just like the individualized trim. But you can also use the value that you've provided.
yes. But we need more investigations and more study, in particularly the next for this study, the second study should be closely the same, but on polyarticular exercises, squats, deadlift, and so on, or weightlifting exercises to check if we still have these relationships. I think yes, but for now, to me, it's a good point of start, and we could start modeling or quantifying, computing training loads using this value.
Okay, great. Okay, thank you. And okay, so does anyone else have any questions from the floor? So Luke, please unmute and
Hi, Luke.
Hi, Frank. It was a pleasure to listen to your presentation and to read the paper beforehand. It was a really good one. Gave me a lot of insight personally for some work. But so back on the equations actually too. This is where I had some questions. The RFD like value, the alpha. You said it works well for applying to anybody. Would it be possible, you think, if you could actually fit it in real time to an individual person using other like measurement devices? So I had thoughts about utilizing a IMU or a linear position transducer to quickly measure the change or the rate of force decay in like an exercise rep to rep throughout a set to get insight on like how the individual is fatiguing and how neuromuscular fatigue is accruing throughout the set. Any thoughts on doing that as like a instead of like using all the really advanced measurement systems?
Okay, if I understand, sorry if I'm wrong, but you ask how did I measure the radical of R&D in the context, or how it could be done in practice, right?
So, yeah, so I'm assuming you measured it using the isokinetic leg extension machine, I presume, correct?
Okay, wait, I will share again. So we computed rate decay of R&D, rate decay of first, okay, RFD here. On each repetition of each series and compute just the slope of RFD, which is rate decay. In practice, with some LPT, you could do the same. So we could have this value and this physiological responses and neuromuscular responses in practice using some wearable systems or LPT, for example. So in our study, we did that on each repetition and each set. I'm sorry if I misunderstood the question, but feel free to ask me again or reformulate maybe. Sorry.
No, it's good. That answers it pretty well. So you use the median frequency this is for EMG,
Yes.
if I'm correct, right?
Yes.
Okay, so
Yes.
if you were to use for full body, then the
Yeah.
EMG like median frequency values would be really difficult to measure, right? Because if you did a squat,
Yes.
you'd have to measure quads, glutes, adductors, and
Yes.
like everything. So do you think it might be better to try to use something like that's more holistic that measures the like overall net change of like moving the external load and how that let me try to read this, how the power output or change in force of the barbell moving or the dumbbells or whatever the equipment is moving would reflect more like systemic neuromuscular fatigue.
Yes. That's why we computed this model. We provided this model based on RFD and not EMG in frequency domain, because as you said, it's really restricted to laboratory conditions and local exercises. So I think RFD, this model based on RFD could be used. Yes, in mostly conditions and mostly exercises using barbells in weightlifting, powerlifting, and so on. So I presented results from EMG only for rigorous and because we were in laboratory conditions, but yes, focus on RFD. Focus on RFD because we know that the rate of force development and the rate decay of force development is a key factor, an influencing factor, a key indicator of muscle fatigue. So this is, I think, the key of the results is the use of RFD.
Okay, cool.
Or other.
Sorry, what was the last part? Just one more quick question on parallel to that. You also created the impulsion training load equation. Is it possible if you go into any more depth on that? Because I know it was kind of like it's mentioned and then it's kind of like not talked about much more. Was it just not super accurate? Did it not have a high predictive value?
Yes. In terms of explanation power, the model with impulsion was not better because I think it's not sensitive enough, or at least it takes all the effort as an integral and it cannot discriminate what discriminates RFD and EMG. So we ask ourselves why impulsion did not provide it so as good as so good results. I don't know. Honestly, I don't know. I think it could be interesting to go deeper, particularly because we have this measure with LPT. So it could be interesting to compute training loads according to impulsion and see and search for relationships and explanation of physiological adaptations. But to date, with this result, I can only say that rate of force development was a bit more significant.
Okay. All right. Thank you.
Perfect. Thanks, Luke. I'm just checking your time. So we're up against about 10:30. So I think what I'm going to do is I'm going to stop the recording now. But just before I do, I want to thank Frank very much for giving us the talk and hanging out with us today. So thanks again.
Thank you.